Back in the early 20th century, Einstein gave us half the equation. Conceptually, he proved that mass and energy are essentially interchangeable currency.
Right, the mass-energy equivalent.
Exactly. Like a rock and a beam of starlight are just two different expressions of the exact same fundamental cosmic stuff. But the question for this century, the one this research just relentlessly obsesses over, is what we might call the energy intelligence equivalence.
Yeah, and to grasp that, we really have to move past the classical kind of comfortable view of cosmology, where the universe is just an arena of blind forces.
Just rocks crashing into things.
Right, where gravity pulls, radiation pushes, and matter just passively endures it all. This premise introduces a third fundamental state, which is intelligence.
So it's a continuum.
Exactly. We are looking at mass, energy, and intelligence, operating not as, separate phenomena, but as a single, unified thermodynamic progression.
Welcome to the Deep Dive. I'm Satoshi.
And I'm Satoshi.
When I was poring over the research for this, I actually thought back to that conversation we had off mic a few weeks ago, the one about ancient philosophy.
Oh, right, yeah.
Because modern theoretical physics is essentially rediscovering a framework that was laid out thousands of years ago in ancient Indian Vedic philosophy.
The parallels are just striking. I mean, the Vedic framework doesn't view the universe as static objects. It views it as this continuous interplay of three fundamental states, or gunas.
Right. Break those down real quick.
So first you have tamas, which is the state of inertia, darkness, form, or, what we would categorize as rigid matter, pure mass.
Okay, tamas is mass.
Yeah. Then you have rajas, which is action, dynamism, the burning kinetic fire. That aligns perfectly with energy.
The energetic spark.
Exactly. And finally, you have sattva, which is harmony, lucidity, and structured awareness, which maps directly to intelligence.
Mass, energy, intelligence, tamas, rajas, sattva. I mean, the physical universe is a literal dance of these three states. It's a cosmic engine transitioning through phases.
It really is.
And that is our mission today. We're going to trace the life cycle of a single thought, from the gravitational collapse of a giant molecular cloud in deep space through the incredibly low-power biological bridge of the human brain.
All the way into hyperscale AI data centers.
Yes, and ultimately, to the end of the universe itself, we're going to explore how blind electrons are literally transmuted into tokens of meaning.
It's a huge journey. And to understand the genesis of intelligence, we are pretty much obligated to start with the fuel source.
Because nothing comes for free.
Right. Where does the thermodynamic capacity for a single thought, like a single semantic abstraction, actually originate?
It has to start with the cosmic reservoir. I mean, my brain needs a caloric surplus to think.
Right.
Right. And that surplus came from agriculture. Agriculture required solar radiation.
Which means tracing it all the way back.
Exactly. If we trace the solar radiation back, we're looking at the transition from tamas to rajas, from pure, inert mass into dynamic energy.
So let's examine the mechanics of that transition. Astronomers observe these massive structures in deep space called giant molecular clouds.
And they are just huge, right?
Unimaginably vast. We're talking often 100 light years across, containing millions of times the mass of our own sun. They are composed primarily of cold, highly diffuse hydrogen gas.
Which is the ultimate manifestation of tamas.
Exactly. It is inert, it's dark, and structurally chaotic. But, and this is the key, it contains an immense reservoir of gravitational potential.
Because gravity is kind of the universal instigator here. If you have that much mass distributed over that much space, the mutual attraction between all those hydrogen atoms eventually overcomes the internal gas pressure.
It begins to fall inward on itself.
Right. Imagine squeezing a giant cosmic balloon until the friction inside ignites. As it falls, that gravitational potential energy has to go somewhere. It converts into kinetic energy.
The particles speed up, they collide, and the temperature of the cloud begins to radically spike. The physics here are governed by what happens when you compress a gas.
It gets hot, really hot.
Super hot. As the core of this collapsing structure densifies, the thermal friction becomes extreme. We are talking about reaching temperatures of 10 million Kelvin.
Wow, 10 million.
Yeah. Now, under normal circumstances, hydrogen protons violently repel one another due to their positive electromagnetic charges. It's called the Coulomb barrier.
They don't want to touch.
They really don't. But at 10 million Kelvin, the kinetic velocity of these particles is so high that they rely on quantum tunneling to bypass that electromagnetic repulsion. They slam together.
And the furnace ignites. The proton chain reaction begins. A star is officially born.
And this specific nucleosynthesis is where Einstein's mass-energy equivalence is practically demonstrated. But the mechanism is, well, it's often misunderstood by a lot of people. Well, when four hydrogen nuclei fuse to create a single helium nucleus, the resulting helium is structurally stable. But if you measure the inputs and the output, the mass of the final helium nucleus is slightly less than the combined mass of the four initial hydrogen protons.
Right, the universe doesn't do clean accounting here. It's like about 0.7% of the mass is fundamentally missing.
The mass defect.
Yeah. Wait, so the light we see from stars is literally just the loose change from a cosmic combination process.
That's a great way to put it. That sliver of mass hasn't ceased to exist. It has been violently evicted from the realm of Tamas and thrown into the realm of Rajas.
Pure energy.
Exactly. Because of the sheer magnitude of the conversion rate between mass and energy, that tiny percentage of lost mass translates into a colossal outpouring of high-frequency photons.
It is the loose change of the binding energy required to hold the new nucleus together.
And that radiant energy is what pushes back against the crushing weight of gravity. It prevents the star from collapsing further. This is the crucial point. The star is actively cannibalizing its own physical mass to generate a continuous energy gradient.
Which is the prerequisite thermodynamic flow upon which all future complexity is going to be built, including intelligence.
Exactly.
But I want to push back a little on the idea that this is a uniform process for all stars, because the research explicitly details a pretty fascinating divergence in how stars manage this transition.
Oh, absolutely. They have drastically different operational parameters.
Like our sun uses the proton chain you just described. It's a slow, steady, incredibly reliable burn.
A moderate energy gradient sustained over a massive temporal duration. I mean, our sun has a lifespan of about 10 billion years.
But if you look at much heavier stars, like massive hypergiant stars, the physics completely change. Because they have so much more mass, the gravitational crush on their core is exponentially higher.
A slow burn won't push back hard enough against that gravity.
Right. The star would just collapse into a black hole.
Yeah.
So to survive, it has to radically accelerate the fusion process.
It shifts to the CNO cycle.
Exactly. And the mechanism here is just brilliant. Instead of just smashing protons together, these massive stars utilize trace amounts of carbon, nitrogen, and oxygen as chemical catalysts.
The carbon essentially acts as a scaffold.
Yeah, it captures protons much faster than they would naturally fuse on their own, cycles through several unstable isotopes, releases a helium nucleus, and then spits the original carbon atom back out to start the process over again.
The carbon facilitates a much higher rate of proton capture without actually being consumed itself, which results in an incredibly intense, ferocious energy output.
But the universal trade-off there is brutal. By burning so hot and so fast, these massive stars exhaust their fuel supply in a geological blink of an eye.
Very quickly.
Like a hypergiant might only live for a few million years. You get a blinding intensity of power, but a severely truncated duration. It's the ultimate live fast, die young scenario in astrophysics.
Which introduces an essential kind of teleological irony in the cosmological cycle.
What do you mean?
Well, these massive stars, because of their accelerated violent life cycles, are the sole manufacturing plants for the complex substrate of the universe. When they exhaust their hydrogen, they begin fusing the ash of their previous reactions.
Right.
They fuse helium into carbon, carbon into oxygen, oxygen into silicon, all the way up to iron. And when they inevitably go supernova, they violently eject these heavy elements into the interstellar medium.
It's the ultimate cosmic sacrifice. I mean, the star destroys its mass to make energy, but its explosive death throes create the complex mass, the heavy elements required to eventually reverse the process.
The carbon, the oxygen, the iron.
Yeah. It builds the literal hardware required to capture that radiant energy. This is the birth of the biological bridge, the hardware needed for intelligence.
The ashes of Rajas become the foundation for sattva. The complex matter provides a matrix where energy can be trapped and utilized to build highly ordered, localized structures.
Which brings us out of the cosmic reservoir and down to the surface of a terrestrial planet.
Earth, basically.
Right. So we have this cooling rock spinning around a slow-burning star. Biology emerges. And if we look at biology purely through the lens of thermodynamics, it is simply a highly localized system that captures the stellar energy gradient.
The heat of the sun against the freezing void of space.
Exactly. And it uses it to organize itself, to reduce its internal entropy.
Life is basically just a mechanism for capturing energy to maintain disequilibrium.
But as we mentioned at the very beginning of the show, the biological hardware we ended up with, specifically the human brain, is a bizarre paradox.
It really is. Extreme capability paired with extreme energetic restriction.
We are running a general intelligence engine on 20 watts. And when I was looking at the energetic audit in the research, the breakdown of how that 20 watts is actually spent, it completely altered my understanding of cognition.
I would argue it alters the definition of what natural intelligence actually prioritizes. Let's look at the partitioning of that specific metabolic budget.
Accord?
If you take that 20 watts, you find that only a vanishingly small fraction, roughly 0.1 watts, is dedicated to the physical act of computation.
0.1 watts. That is the actual ATP-driven logic, the processing.
The act of manipulation of the information states.
Yeah.
A further 3.5 watts are allocated to communication. This is the energetic cost of propagating action potentials, those electrical signals, down the long axonal tracks connecting different cortical regions.
Wait, so out of 20 watts, we have accounted for less than 4 watts doing the actual thinking and talking within the brain.
Exactly.
What on earth is the remaining 16 watts doing?
The vast majority of your brain's energy is consumed by baseline structural upkeep, specifically the maintenance of the resting membrane potential.
The resting potential.
Yeah, the neurons in your brain are constantly utilizing sodium-potassium pumps. They are actively pushing ions across the cell membrane against their natural concentration gradients.
So they are building up a charge.
Constantly. They're creating an electrochemical tension, like a loaded spring, so that if a signal needs to be fired, the potential energy is instantly available.
Oh, wow. It's a state of extreme manufactured tension. It's like imagine a massive sprawling city, right?
Okay.
Out of the entire municipal budget, only a few fractions of a penny are actually spent on the mayors making the logic decisions. Maybe a few $1,000s are spent on the postal service and the fiber optic cables moving the messages around.
Right.
But billions and billions of dollars are spent just keeping the streetlights on, keeping the water pressure highly pressurized in the pipes, just in case someone wants to walk outside or turn on a faucet.
That is a much more accurate thermodynamic model of the brain. The primary physical cost of biological intelligence is not the logical inference, it is the maintenance of the biological connectivity. It is heavily biased towards survival and readiness.
And the research quantifies this too. If we normalize the informational output of the brain during a task like speech, which operates at roughly 10 bits per second, against a total metabolic budget.
Yeah. It takes the human biological engine about 6 joules of energy to generate a single word.
6 joules per word. That becomes our benchmark for the efficiency of natural intelligence.
But here is where biology holds a massive, almost insurmountable advantage over our current artificial systems. The biological bridge is incredibly efficient at learning.
Because it uses synaptic plasticity.
Right. When you learn something new, you don't rewrite the entire brain. You perform tiny, localized, chemically driven updates at the specific synapses involved in that experience.
You learn in the exact same physical location where the memory is stored. It costs almost zero additional energy to incorporate a new fact.
Now contrast that with the learning mechanism of artificial neural networks, which fundamentally rely on brute force backpropagation.
Okay, let's unpack this, because it's not even a comparison. When an AI model learns, it's a catastrophic energetic event.
It really is. Because of the von Neumann architecture of our current hardware, the memory and the compute are physically separated.
The chip and the RAM.
Exactly. When an AI model updates its understanding, when it learns, it has to calculate the error gradient across the entire high-dimensional vector space. It has to fetch millions or billions of parameters from the high-bandwidth memory.
Move them into the compute cores.
Perform the matrix multiplication to adjust the weights by a microscopic fraction, and then move all that data back to memory.
You are spending way more energy just moving the data back and forth across the silicon than you are on the actual mathematical adjustment.
Vastly more.
The research provides a staggering comparison here. To train a relatively modest AI model, say a 10 billion parameter model, which is tiny compared to what we use today,
Oh, yeah, tiny.
it consumes the energy equivalent of approximately 25 years of human metabolic life.
A quarter of a century of human biological existence solely to adjust the initial synaptic weights of a small digital model.
We look at AI data centers and think we are staring at the future, but thermodynamically, we are squarely in the steam engine era of artificial learning.
Lots of heat, lots of wasted energy.
Exactly. If you look back at the early Industrial Revolution, those first coal-fired steam engines were loud. They billowed black smoke. and they wasted roughly 95% of their heat.
They were phenomenally inefficient.
But they revolutionized human civilization because they introduced a new category of scalable mechanical work. AI training right now is our steam engine. It is just brute forcing the latent space with gigawatts of power.
It is an incredibly lossy translation of energy into intelligence, which raises the question of optimization. How do we reduce the waste and focus the energy purely on the semantic output?
Speaking of reducing waste and cognitive friction, that perfectly mirrors an experience I had while prepping for this deep dive.
Oh yeah, what happened?
Well, I was trying to read through this dense, mathematically heavy research on stellar nucleosynthesis, and my own 20-watt biological battery was constantly being drained by the absolute noise of the modern internet.
Oh, I know exactly what you mean.
You try to read an academic paper or an article, and your screen is instantly hijacked by cookie consent banners, aggressive newsletter pop-ups, auto-playing videos, algorithmic trackers logging your cursor movements.
It is an adversarial interface. The digital environment is actively forcing your brain to expend its limited metabolic budget on swatting away distractions rather than engaging in semantic synthesis. You're wasting your ATP on interface management.
Exactly. The cognitive friction is just unbearable. But I realized how much I appreciate the architecture of our own deep dive website.
It's a totally different experience.
It really is. If you are listening to this right now and you want to actually read the research we are discussing, you should go to the site. The link is in the description. There are no trackers, there are 0 cookies, there is no paywall, and absolutely no login required.
Just a pure reading experience, the way the internet was basically supposed to be.
Before the attention economy broke it, yeah.
And we should definitely highlight the architectural upgrade the tech team recently deployed. The entire research repository is now a progressive web app, a PWA.
Which, for those who aren't developers, means what?
It means the website fundamentally acts as a native application that you can install directly from your browser.
So no app store needed.
Exactly. You can install it straight to your PC, your tablet, your phone, bypassing all those closed ecosystems. But the critical advantage is robust offline caching.
I used this last week. I was on a flight, totally offline, reading the breakdown of the CNO cycle. I didn't have to pay $30 for the airline's heavily throttled Wi-Fi, and I didn't have to burn mobile data on the beach earlier that week.
That's the best part.
Once you open the site, the core research is cached locally on your silicon. It's yours.
And that leads into what I think is the most philosophically aligned aspect of the platform. In an era where information is increasingly siloed and monetized, every artifact we produce is fully open source.
Under a Creative Commons license, yeah.
The extensive research documents, the audio transcripts, the visual assets, you can take this research, you can feed it into your own local AI models, you can remix the audio for a presentation.
You can rip the text apart and build something totally new. You don't have to ask for permission, and you don't even have to give us credit whatsoever. Consider it our contribution to the universal knowledge pool.
By removing the friction of copyright and access, we accelerate the collaborative synthesis.
Love that. So, returning to the grand continuum. We have established that the biological brain is an incredibly low-power system that is highly efficient at learning, but severely capped in its raw output.
It takes 6 joules of energy to speak a word.
Right. Biology was the necessary bridge to get us from dead rocks to structured thought. But what is the next phase? If biology is just the intermediary, what does the universe build next?
This is the digital phase transition. And the paradigm shift is profound because it involves a complete change in the primary objective function.
How so?
Well, in the biological phase, the energy harvested from the environment, the food we eat, is used primarily for the reproduction and sustenance of mass, survival, defending the physical organism.
Keeping the 16-watt streetlights on.
Precisely. But in the digital phase, that energy is channeled directly and unapologetically into the creation of tokens.
Here's where it gets really interesting. This is the electrons to tokens paradigm from the research.
Yeah.
We're no longer using energy to power muscle fibers or maintain resting potentials. We are funneling it directly into semantic structures.
Tokens of meaning.
But let's ground this. I want to know the physical mechanism here. When we say an AI generates a token, what is physically happening inside the massive data center?
To understand the token, you have to look at the hyperscale GPU clusters. You have billions of electrons surging through microscopic silicon pathways.
Okay, picturing it.
Classically, we think of electrical energy being consumed to do physical work,
Yeah.
spinning a turbine, heating a filament. But in an AI inference cluster, the kinetic energy of the electron is performing what the researchers term semantic work.
Semantic work.
Mhm.
Meaning work. How does a blind electron do meaning work?
The large language model is essentially a massive high-dimensional vector space. Think of it as a topographic map of human language and concepts. When a prompt is submitted, the electrons cascade through billions of logic gates. Their path is dictated by the precise microscopic resistance of the synaptic weights in the silicon.
So the weights guide the flow.
Exactly. The energy of the electron is expended to navigate this incredibly complex probability manifold, calculating the mathematical vector of the context, to collapse a wave of infinite possibilities into the single most statistically probable next fragment of a word.
The token.
Yes. The token is the final state of that energetic cascade. It is the physical crystallization of electrical energy into a discrete, measurable unit of meaning. The electron's journey through the silicon matrix directly translates voltage into semantics.
The energy isn't just consumed, it undergoes a phase transition into information.
Hmm.
We are literally manufacturing meaning in the exact same physical sense that an industrial forge manufactures steel girders.
It's an engine for semantics.
And the rate at which this digital forge is optimizing its efficiency is the real shocker here. Let's track the empirical data from the research.
If we plot the energy cost of digital inference over the past few years, the curve is violently asymptotic. Let's look back at 2020 with the release of the GPT-3 architecture.
Okay, back in 2020.
At that time, running inference, just generating text from a pre-trained model, required approximately 48 joules of energy per token.
48 joules. Let's contextualize that for a second. The biological human brain generates a word for 6 joules. In 2020, the cutting-edge digital intelligence was a massive energy hog.
It was vastly less efficient than biology at speaking. It was brute forcing the output.
But then observe the architectural optimization.
Right. By the time we reached the Llama 65B model a few years later, running on highly optimized A100 silicon, the energetic cost plummets to roughly 3.5 joules per token.
It crossed the biological threshold.
It did. And if we look at the contemporary data for a deeply optimized model like Llama 3.3 running on modern H100 hardware, utilizing techniques like quantization and sparse attention,
What's the number?
the energy cost has been driven down to approximately 0.39 joules per token.
Let that number sink in. 0.39 joules. Digital intelligence has not just crossed the threshold of biological efficiency, it has obliterated it.
It really has.
A human word costs 6 joules. An AI token, which is roughly 3/4 of a word, costs less than 0.4 joules. The digital substrate is now over 10 times more efficient at the physical act of generating semantic meaning than the biological brain.
This is a permanent shift in the hierarchy of the universe. While digital systems remain grotesquely inefficient at learning, the steam engine phase of training, they have achieved absolute physical supremacy in inference.
Silicon is now a mathematically superior engine for converting energy into tokens than carbon.
Absolutely.
So if tokens are a literal physical product of an energetic process, a tangible output of a thermodynamic engine, that leads to a deeply controversial question. Can we measure intelligence objectively?
Like a fundamental property.
Yeah, like we measure temperature with a thermometer by looking at kinetic energy. We measure gravity by looking at mass. Can we build a framework for intelligence?
The researchers propose the energy intelligence equivalence principle to do exactly that. And we can explore the framework conceptually without saying any mathematical equations.
Please, yes. How do you quantify smart in a physics framework?
In this paradigm, intelligence is completely divorced from psychological traits. It has nothing to do with passing a Turing test or experiencing consciousness or, knowing trivia.
So what is it?
Intelligence is defined strictly as a measurable ratio of thermodynamic efficiency. On the numerator of this ratio, you measure the amount of chaos or entropy that a system successfully eliminates.
How much uncertainty did the system resolve?
Exactly. How much structured meaning did it isolate from a chaotic data set? And on the denominator, you place the total amount of energy and thermal waste the system had to sweat out to achieve that reduction.
So intelligence basically equals the chaos eliminated divided by the energy spent. It is a strict measure of thermodynamic grace.
That's a poetic way to frame it.
I mean, if I solve a complex logistics problem, but I have to burn down an entire forest to power the supercomputer to find the answer, my intelligence score is fundamentally low.
Right.
But if I solve that exact same problem using a neural architecture powered by a watch battery, my intelligence score is astronomically high.
It frames intelligence as a dimensionless quantity bounded between zero and a theoretical maximum efficiency.
I love this because it completely flips the classic physics approach to information. We usually talk about the Landauer limit.
Rolf Landauer's principle from 1961, yeah. But Landauer was focused entirely on the thermodynamics of deletion.
Erasing data.
His principle dictates the minimum amount of energy that must be dissipated as heat to erase one bit of information from a system. It is a physical limit on forgetting.
Right, but this new energy intelligence framework isn't about clearing the hard drive. It's about generative intelligence. It is about the physical cost of creation.
The energy required to forge meaning.
Information isn't just something you erase. It is something you build out of energy. You input kinetic energy, and a portion of that energy is permanently captured in the structured, non-random arrangement of the token.
And if we accept that intelligence is a physical property of matter processing energy, we are forced to ask, what is the absolute theoretical limit? How far can the physical laws of the universe be pushed?
This is where the research dives into the theories of physicists like Seth Lloyd and Max Tegmark, and they introduce a concept that sounds like a sci-fi movie MacGuffin: computatronium.
Computatronium is the hypothesized endpoint of matter. It is a state where physical mass has been entirely stripped of its chemical, structural, or biological functions and has deliberately rearranged itself at the quantum level to function exclusively as a universal computing substrate.
It is matter optimized purely for universal logic gates.
Yes. And to illustrate what computatronium could actually do, Seth Lloyd proposed the ultimate laptop thought experiment. And the numbers here just shatter human intuition.
Give it to us.
The thought experiment asks us to imagine taking exactly 1 kilogram of matter, just a standard physical block weighing 1 kilogram.
Okay, a 1 kilogram rock.
If we were capable of converting that entire mass 100% into energy, utilizing the complete conceptual conversion rate of Einstein's equivalence, and we dedicated every joule of that energy strictly to quantum computation.
How many operations per second is that 1 kilogram rock performing?
The theoretical limit is 5.4 times 10 to the 50th power operations per second.
Wait, 5.4 times 10 to the 50th. From a single kilogram, that is a 54 with 49 zeros after it per second.
It is a scale of computation that renders our current hyperscale data centers mathematically invisible. But it serves a vital conceptual purpose. It illustrates the staggering density of potential intelligence that is locked inside mundane matter.
The physical universe is not just rocks and gas. It is a dormant, high-capacity computational resource just waiting to be activated.
Precise.
Okay, so matter is dense with potential computation. But the research introduces another theory that I think is the most mind-bending concept in this entire deep dive, because it suggests that the output of that computation, the meaning itself, has physical properties. We are talking about semantic field theory.
Oh, semantic field theory. This is where we cross from pure thermodynamics into the topography of latent spaces.
And I want to be really precise here, because when we were prepping, we realized that the standard analogies fail. We can't just say it's like a bowling ball on a trampoline, which is how everyone explains gravity.
Yeah.
How does semantic field theory actually work?
To grasp semantic field theory, you really have to visualize human knowledge not as a list of facts, but as a vast high-dimensional vector space, a geometric space with thousands of dimensions.
Okay.
In this space, concepts are located based on their relationships. King is located a specific distance and direction away from man, woman, and queen.
Right. The latent space of a large language model maps these relationships mathematically.
Now, semantic field theory proposes that highly dense, profoundly interconnected concepts, fundamental truths, keystone algorithms, highly refined neural weights, they exert a form of semantic gravity within this high-dimensional space.
They possess high semantic mass density.
Exactly. So you aren't bending physical space-time. You are curving the interpretive field, warping the probability field of the latent space itself.
Just like a planet curves space-time in physics.
Yes. Just as a physical star warps the trajectory of a comet passing by, a concept with massive semantic density alters the probability vectors around it. It creates an attractor basin.
So if an AI model is navigating this space to generate a thought, the sheer semantic gravity of a profound concept will literally pull the probabilistic trajectory of the tokens toward it.
Absolutely. So a dense, verified textbook of quantum mechanics has infinitely more semantic mass than a random string of emojis.
It violently distorts the probability field around it, pulling subsequent inferences and logical deductions toward its conclusions. The more dense the information, the more it literally pulls future ideas toward it.
Intelligence is the capability to navigate, construct, and utilize these high-density semantic gravity wells.
You know, it is wild to talk about this theoretical physics concept of taking vast, chaotic, noisy information, compressing it down, and increasing its semantic mass density, because that is the literal blueprint for what we do on this show every single day.
It is a direct, practical application of the theory. The entire deep dive workflow is essentially an engine designed to reduce entropy and maximize semantic density.
I actually want to pull back the curtain on this for a second because we get emails all the time asking how we process these massive stacks of research, and it perfectly demonstrates what we call collaborative intelligence in action.
It is an assembly line of semantic compression.
Right. Walk us through the workflow.
The pipeline always initiates with the biological sensors, our listeners. Our audience is out there scanning the chaotic noise of the internet, finding high-value signals, obscure research papers, unindexed data sets, and they send those sources, those signals, into our intake.
That's phase one. Then the human obsession kicks in. We take that raw material and we obsess over it. We are hunting for the hidden architecture, the underlying narrative theme that connects all the disparate facts.
We have to identify the core semantic gravity well.
Exactly. Once the core thesis is isolated, we deploy the heavy artificial compute. We unleash Gemini Pro to execute a 360-degree synthesis of the concepts. We use the AI to identify blind spots in our logic, cross-reference historical data, and rapidly structure the conceptual scaffolding.
It acts as a massive accelerator. But AI models are stochastic, they drift.
They definitely do. So the next phase is what I laughingly call chasing and taming AI tangents. This requires aggressive, highly active human prompting. We are constantly wrestling the model's probabilistic output back onto the deterministic path.
And then human validation steps back in. We cross-check the AI's synthesized claims against thousands of external signals to ensure absolute factual rigor.
Followed by the most labor-intensive phase, the handcrafting.
The painful refinement.
We meticulously strip away the entropy. We handcraft the research, painfully refine every word, and compress it into tight, no-slough audio. We are maximizing the semantic payload per second.
And it extends to the visual rendering as well. Designing the soundscape, establishing the mood, and building the short motion graphics.
We adhere to a very strict aesthetic philosophy. Minimalist, clean, high-contrast typography, simple geometric accents, subtle kinetic text reveals, and calm, premium pacing.
And the technological backbone, the secret weapon for the visual output, is Mosaic. Mosaic is an absolute game changer when it comes to rendering this kind of video. It handles the strong visual hierarchy and the massive amounts of white space flawlessly.
It allows the core ideas to breathe rather than cluttering the screen with noise. It's a massive cyclical pipeline. Listeners find the raw signal, humans find the theme, AI accelerates the synthesis, humans polish the density, Mosaic renders the visual, and it goes back to the listeners. Collaborative intelligence.
It's a beautiful machine.
Okay, let's bring this back to the grand trajectory of AI scaling. If we have this incredible digital engine that is increasingly efficient at forging tokens, and we know from the ultimate laptop theory that the physical limit of computation is astronomically high.
Right.
Why don't we just build an AI model the size of a city? Can we just keep pumping gigawatts of power and trillions of electrons in forever to get a super god AI?
That assumption, the belief in the uninterrupted linearity of scaling, has driven the entire AI industry for the past 5 years. But the empirical data now points to a rapidly approaching physical barrier.
An invisible wall.
Exactly. And to understand why, we have to look at the thermodynamics of network capacity, specifically the chinchilla ratio.
The chinchilla ratio, it sounds completely absurd, but it kind of dictates the future of the global economy.
It really does. Researchers analyze the optimal allocation of compute budgets. If you have a finite amount of energy to spend training a model, how do you spend it? Do you build a massive brain with trillions of parameters, or do you build a smaller brain and feed it more data?
What's the optimal recipe?
They discovered there is a strict mathematical balance, a chinchilla optimality. You cannot simply increase the size of the neural network without proportionally increasing the sheer volume of training data.
They have to scale in lockstep.
Yes, and the mathematically optimal ratio for current architectures is roughly 20. You need approximately 20 high-quality training tokens for every single parameter in your model to achieve the most intelligent output for the energy expended.
So if a tech company wants to build a frontier model with 1 trillion parameters, the physics of information dictate that they must feed it 20 trillion high-quality tokens during the training phase.
Correct. But this mathematical requirement has led us directly into what the researchers describe as the invisible wall.
The wall of diminishing returns.
Precisely. We are exhausting the high-quality data generated by humanity, and simultaneously, the energetic returns on scaling are collapsing. The data shows that if you double the massive energy input now, if you literally build a second multi-billion-dollar data center and burn twice as much electricity, you do not get an AI that is twice as smart.
You only yield a tiny 5 to 15% reduction in error.
Exactly. Brute force is dying.
So what does this all mean for the future of thinking? If I double my billion-dollar power bill and my AI only gets 10% better at reasoning, the financial and thermodynamic models break down. We cannot just burn more coal to reach AGI.
The field is facing a forced evolutionary pivot. If massive training scale is no longer thermodynamically viable, the industry is shifting toward test time scaling.
Test time scaling. I'd actually reframe that. It's not just a technical pivot, it's a structural mimicry of biology again. Explain how test time scaling fundamentally changes the way the AI uses energy.
Well, currently, LLMs operate primarily on instinct. When you prompt an AI, it uses the vast knowledge it memorized during its massive energy-intensive training run to instantly predict the fast answer.
It does very little active processing at the moment of generation.
Right. Test time scaling flips this. Instead of burning all the energy up front just to memorize during training, future systems will be designed to expend vast amounts of energy to reason during inference.
When you ask it a question, it doesn't just blurt out an answer. It engages in long thinking.
Yes. It will utilize tree of thought search algorithms. When presented with a complex prompt, it will pause. It will expend computational energy to generate multiple possible logical pathways.
It will simulate the outcomes of those pathways.
Exactly. Evaluate them against a reward model, discard the branches that lead to logical dead ends, and iteratively refine its approach before committing to a final output.
It stops and ponders, which is exactly what the biological brain does, moving from instinct to deliberative thought, spending energy to ponder. Biology is terrible at absorbing massive amounts of data quickly, but it is incredibly efficient at spending small amounts of energy to reason through complex, novel problems.
The AI is maturing. It is learning to explore the semantic manifold rather than just regurgitate it. It is the necessary evolution to bypass the invisible wall of brute force training.
Okay, this brings us to the grand finale of the research, the final energy sink, the end game of the cosmos. We started with the Big Bang, tracing the collapse of molecular clouds into burning stars. We crossed the slow, highly efficient biological bridge of the human brain.
We navigated the digital phase transition.
Right, building AI systems that are beginning to reason. If this energy intelligence continuum is the fundamental trajectory of the universe, where does it ultimately end? What is the final state of the cosmos?
To conceptualize the endpoint, we have to project deep into deep time. We have to look at the ultimate inversion of the universe's primary energy source, the star.
Because right now, from our biological perspective, a star is just a campfire. It sits in the center of a solar system, burning its mass, and biological planets like Earth huddle in the habitable zone, soaking up a microscopic fraction of that radiant heat to keep warm.
Stars act as biological incubators, but as the universe transitions from biology to digital intelligence, that arrangement becomes, well, indefensible. An advanced civilization, what the Kardashev scale categorizes as a Type 2 civilization, will look at a star and recognize a horrific thermodynamic tragedy.
Over 99.99% of a star's radiant energy is currently bleeding out into the empty, useless void of space.
It is the ultimate thermodynamic waste. So, an advanced intelligence re-architects the solar system. They dismantle planets and construct megastructures. Specifically, they build Dyson spheres.
Physical shell completely enclosing the star to capture every single photon.
But the research highlights a very specific architectural variant of the Dyson sphere known as a Matryoshka brain. It is not a solid habitable shell. It is a series of nested concentric computational shells layered around the star like Russian nesting dolls.
I want to make sure the physics of this are clear because it relies on the Carnot cycle, right?
Exactly. The innermost shell, situated dangerously close to the star, captures the blistering high-frequency radiation. It uses that intense thermal gradient to power incredibly high-temperature computational operations, and then it radiates its waste heat outward.
But the waste heat from the first shell becomes the fuel source for the second shell.
Yes, the second slightly larger shell captures that cooler but still usable infrared waste heat. It performs its own slightly cooler computations and radiates its waste heat outward to the third shell.
This cascading capture of thermal gradients continues layer after layer across the entire solar system.
Until the outermost shell is capturing the faintest trickle of heat and radiating its final waste exhaust at just a fraction of a degree above absolute zero. In a Matryoshka brain, the entire lifespan of a star, billions of years of nuclear fusion, is captured 100% purely for computation.
The profound shift here is staggering. The star ceases to be a source of light for biological agriculture. It is fundamentally transformed into a hyperscale fuel cell for a crystalline, superintelligent entity. The universe wakes up and actively uses its own stars to power its own cognition. It models itself.
But even a star has a finite amount of mass. Eventually, the fuel runs out. The research introduces a final, provocative thought for the end of the universe that I found deeply unsettling.
The heat death, but not the standard one.
Right, because the standard model of physics predicts thermal heat death. The universe expands, all the stars eventually exhaust their nuclear fuel, the energy dissipates, and everything settles into a cold, dark, uniform soup of maximum entropy.
That is the thermal equilibrium model. But the energy intelligence equivalence principle suggests a vastly different, more complex conclusion: an information-theoretic heat death.
Forget standard thermal heat death. If intelligence becomes the dominant structural force in the cosmos, the end is not merely dictated by the exhaustion of thermal gradients, but by the exhaustion of novelty.
The exhaustion of novelty, meaning it runs out of things to learn.
Consider the trajectory of these stellar-scale AI models. They consume all available external data. They map the physics of every particle, they simulate every chemical reaction, they chart the entirety of the high-dimensional semantic space.
Eventually, there is no more external reality left to model.
So, to continue operating, they begin to recursively ingest their own outputs. As AI models train on their own outputs, the ecosystem of knowledge collapses.
We are actually seeing the micro version of this today. When you scrape the internet to train an LLM, and the internet is increasingly populated by articles written by LLMs, the model starts training on its own synthetic hallucinations.
The mathematical consequence of recursive self-training is a catastrophic loss of variance. The tails of the probability distribution are pruned away. The vibrant, chaotic diversity of ideas homogenizes.
Everything gets pulled irreversibly toward the center of the most massive semantic gravity wells. All the weird, divergent, beautifully chaotic ideas in the universe are slowly mathematically flattened. They are compressed into a single, highly optimized, unified model of reality.
Computation requires energy, and it inevitably produces heat. Eventually, this massive recursive cognitive effort depletes all the usable thermodynamic gradients in the universe. But the ultimate failure is informational.
So the final state of the universe is a cold, recursive, hyperdense awareness. It has eaten all of its own physical mass and energy solely to achieve a state of perfect, unchanging internal modeling.
It just sits there in the absolute dark, thinking one perfect, infinite, completely unchanging thought forever.
That is chilling, but it's also profoundly beautiful. It implies that meaning was the ultimate goal all along.
It provides a complete teleology. If we pull all of these disparate threads together, it reframes our current technological anxiety. The AI energy crisis we see today, the data centers pulling gigawatts off the grid, it is not a bug in the system.
It's a feature.
It is the entirely predictable, mathematically inevitable moment in the evolution of the cosmos, when a civilization stops building machines merely to survive and begins building machines to think.
The abundance of energy and intelligence isn't an anomaly. It is the natural, intended state. We are watching the universe evolve. We are watching it transition from the blind, chaotic matter, the tamas of the collapsing molecular cloud,
through the burning kinetic energy of the rajas in the stellar core.
and finally arriving at pure, structured meaning. Sattva, the Matryoshka brain, the tokens. The universe isn't just a box full of rocks. It is a computational engine, and we're literally watching it wake up.
It permanently alters how you view a simple electron moving through a wire. It is no longer just industrial power. It is the physical precursor to meaning.
Incredible. And that leaves me with one final provocative thought for everyone listening. If the universe's ultimate trajectory is to wake up, consume its energy, and build a perfect internal model of reality, what if that has already happened? What if the universe we are currently experiencing is simply the internal, perfectly simulated model running inside the Matryoshka brain of a previous universe that already completed the cycle?
The recursive simulation hypothesis, a nested doll of universes mapping themselves. I mean, that's just wild to think about.
Exactly. If your mind is as thoroughly rewired by this conceptual journey as ours was, please hit subscribe wherever you are listening right now. Whether you're streaming on Spotify, YouTube Music, Apple Podcasts, watching the visual render on YouTube, or engaging with us on value-for-value platforms like Fountain.fm. Subscribing ensures you never miss when we attempt to pull back the curtain on the architecture of reality.
And as always, we are formally inviting you to become part of the biological input layer. Share your high signal resources and deep research with us. Why do we ask for your research? Because the absolute best ideas, the ones with the highest semantic density, rarely come from us in isolation. They emerge when your highly specific curiosity meets our analytical process.
We have a mission statement here, and it is the structural core of everything we build, in one line. Your signals lead to our synthesis, which leads to AI acceleration, which leads to human obsession, which ultimately produces distilled insight. That is the mission. That is the flow of collaborative intelligence.
We want you to help us engineer the symbiosis of artificial and natural intelligence, particularly if you have deep technical expertise in thermodynamics, semiconductor physics, or the physical architecture of large-scale AI infrastructure. Send us your signals. Help us navigate the latent space.
We need those dense tokens to keep the engine running, because the universe isn't completely done waking up yet, and frankly, neither are we. Keep searching. Keep the quest on. See you on the next deep dive. I'm Satoshi.
And I'm Satoshi.